All right, we'll continue on here. Any questions? All right, here's another example you can work out.
Do you want us to try that right now? Or
No. Just try it at home. Here's another one. This one's a bit trickier. Ethanol doesn't appear on the chart. Those are examples of the chart method plus an extension of the chart method. There's more advanced charts called potential diagrams. Potential diagrams we can look at, for example, for manganate. Manganese is very interesting redox chemistry. For example, we have purple for manganate, green, MnO4 2-, black MnO2, red Mn3+, pale pink Mn2+, and manganese metal. And so it has different stages of oxidation. That is, you can have complete oxidation. Complete oxidation would be out the permanganate, or some partial oxidation, starting with manganese. Now, the same thing happens like in combustion, like complete combustion versus partial combustion. Partial combustion, you can end up with soot, carbon particles, or you can end up with carbon monoxide. And so it depends. A lot of redox depends on the conditions. For example, when you burn something, does it always go complete combustion? No, it depends on temperature, concentrations, this type of stuff. Is that stuff that's easy to calculate? If somebody asks you, I want you to calculate how much carbon monoxide I'm going to burn under these conditions, could you do that for me? And so a lot of these redox, they're kind of complicated. So what you do oftentimes is just mix it together and see what happens. Or, a lot of these things, because it would be a huge time saver if you could just go ahead and calculate. Let's say I wanted to produce this much carbon monoxide. How would I do that? How would I get the right conditions to produce that much carbon monoxide? Well, it would be nice to just whip up a calculation and be done with that. But a lot of redox, what they do is they have these little reaction vessels. This happens for all of chemistry. These little reaction vessels that have, actually, we have a small version of that here. This is called a spot plate. A spot plate allows you to do 3, 6, 9, 12 reactions at the same time, kind of. Just on a very small scale. Yeah, and that way you could adjust the conditions slightly and see, how that changes the products. And so this is just the trial and error method. You just try it and see what happens. Well, they have these things where they could fit not just 12, they could fit thousands. And they have it such small scale, miniaturized reaction plates. And so they can do thousands of reactions pretty much at the same time and see what happens. Figure out the best combination of stuff. And so a lot of chemistry is still done that way. We don't use these charts to predict. You could use these charts. We'll look at these charts later. Potential diagrams. Or maybe we don't even look at those. But a lot of redox is still done this way. This is called the skeleton redox. In skeleton redox, you just mix it together and see what the major products formed are. Balancing skeleton redox, this is in chapter 5, so this is just Chem 1A. I think at the end of chapter 5 they talk about this, so go back and review these rules here. But skeleton redox is quite a bit different. Skeleton redox is like this. You just mix it. Okay, when we burn ethanol, do you have to burn it in oxygen? Could you use some other oxidizer to burn ethanol? Is it possible to use another oxidizer in place of oxygen, like burn ethanol in an oxygen-free environment? It doesn't seem so, right? Because you need oxygen to burn things, right? But you don't. Because oxygen, all it is an oxidizer. So you can just use some other substitute oxidizer like fluorine. If you mix ethanol with fluorine, you're going to have a bad reaction. Very bad reaction. But it depends on the conditions, because if you mix ethanol with just trace amounts of fluorine, are you going to have a bad reaction? No? Probably not notice much. If you mix ethanol with highly concentrated fluorine, are you going to have a bad reaction? Yes. And so it depends on the conditions. And so normally when you burn ethanol, what does it form? It forms CO2 and water if you burn it in oxygen, right? Well, for example here, are we completely combusting? Are we completely oxidizing the ethanol? Take a look at that. Like, for example, if you have some wine, and your wine starts, if you drink wine, but if your wine starts to taste like vinegar, you know what just happened? Yeah, your ethanol in the wine was oxidized to, vinegar is acetic acid. And so the ethanol was converted into acetic acid under mild oxidizing conditions. And so that's what happened. So maybe a little bit of air leaked in there, oxidized the ethanol, but it didn't completely oxidize it, it only oxidized it to acetate. And so under these conditions, permanganate's a very powerful oxidizer, but maybe under these conditions, under basic conditions, there's no H+, it only goes to acetate, not CO2. You'd expect ethanol to go all the way to CO2 when it combusts, right? This is an alcohol. And so this is a case where you just mix it together. Maybe you don't want to. Maybe you want to form acetate and not CO2. But typically you would form, when you oxidize ethanol, you would form CO2. And so what we do is we break this up into half reactions. Ethanol goes to acetate, permanganate goes to MnO2 under these conditions. But you know, permanganate could have gone to a lot of different things. Right? Permanganate could have gone to MnO4 minus, could have gone to MnO2, which it did, or it could have gone to Mn3 plus or Mn2 plus, or all the way to manganese metal. It depends on the conditions that you reacted. Well, with skeleton, just mix it together and see what happens. You mix it together and see what happens, but you don't have the whole picture. And so all you have to do is, you don't have to predict the product in skeleton. All you have to do is balance the equation. To balance the equation, we split it into half reactions and then balance those individually. You guys remember that from chapter 5? And so this I'm not going to spend any time reviewing, other than what I just said. And so basically, this is our goal in understanding we want to understand chemistry. Well, chemistry is just not only physical properties, but it's also chemical properties. And we need to understand those chemical properties based on, hopefully, composition and structure. Matter makes up the universe, so an understanding of the theory and the facts of nature, its composition, structure, and properties will help you better understand, the world around you. It's made up of. So, unfortunately, this takes a lot of time and energy to learn. So that's the review of reactions here. So what else are we doing? Okay. Let's see how far behind. Yeah. Oh, not far behind. There's some bleed over. I'm going to have some bleed over here because I didn't want to add in. So chemical reactions review. So we're going to talk about chapter 24, just part point 1 through point 3. And so just 3 sections of chapter 24. The purpose of just this initial talk of chapter 24 is to learn about these species called complexes. And so, if you've ever looked at the acid chart in our room, you would have seen 2 unusual ones that you would have gone, those look very weird. Have you ever looked at the acid chart in our room and seen this one? This acid here turns out to be more acidic than acetic acid. Next time you're in the room, look at the acid chart and see if you could see this. Right? It's a weird one, right? It's a weird one. So how is this an acid? And what is it? You know, it's kind of weird because, well, what this is this is called a complex cation. There's another one that's kind of weird. This is also a pretty good acid too. This is a complex cation. Now, it's kind of weird because, you know, what's going on here? Isn't this just Al3 plus Aq? Well, Al3 plus Aq is this. You know that? And this is Fe3 plus Aq. These weird species also occur on the acid chart that I handed out on Piazza. And so now let's talk about what these weird species are, because is sodium. Oops. Is sodium plus Aq just really NaH2O6 plus? It turns out no, it isn't. And so this is what's going on with these species. When I think about sodium plus Aq, I think of a positive ion that has been, it's going to be stabilized by having water molecule. In other words, we call it a hydrated ion. And so this is not. This is what we call a hydrated ion. Is this a hydrated ion? Not really. I mean, it is hydrated, but really this is a complex ion, not a hydrated ion. And so what's the difference between these two? The difference between these two is this. In the hydrated ion, what's the interaction, what's the attraction between a sodium and the water? What kind of intermolecular attraction is that? What do you call that kind of attraction?
Electrostatic.
It's electrostatic attraction, and if we wanted to label it, we'd call it what? The attraction that holds the water and the ion together, or stabilize it, is called a London force, dipole. No, this is called an ion because it's a full charge. Ions are full charge, and so it's even better than a dipole. A dipole is a partial charge, and an ion is a full charge. The bigger the charge, the stronger the attraction. But water is not a full charge. Is that a full negative charge on the oxygen? No, it's a partial. And so we call it an ion dipole attraction. It's an IMF. And so how many water molecules can we fit around a sodium ion? About 6. And so they're going to be about 6. Are they fixed on? No. What happens is we have something called chemical exchange, where a water molecule comes and bumps this one out, right, and replaces it. You know, the water molecules are constantly moving around, kinetic energy. Over here, this is quite a bit different. When we look at the aluminum and look at the interaction between aluminum 3 plus and water, it looks very different. In fact, aluminum 3 plus actually has a bond here. And so we actually, in this, we actually have 4 waters that are covalently bound in the plane. Oops. Like this. And then we have 1 water sticking out that's bonded. I'll just write OH2 here. And then 1 water that sticks in. OH2, I'll write it because the oxygen bonds to it. And so altogether we have 6 water molecules that are actually bonded to the aluminum metal via a covalent bond. That's really weird because normally when you think about a non-metal bonding with a metal, it's an ionic bond, right? But this one turns out to be a covalent bond. Remember what you guys... Oh, did I forget to record this? No, I'm recording this. Remember what you guys learned about bonding? What types of bond? What are the 2 types of bonding theory that we have? We have MO and valence bond. Valence bond fails for oxygen. Valence bond fails for complexes. We don't use valence bond to describe the bonding in complexes. It just doesn't work. We have to use what to describe the bonding in complexes? We must use MO theory. Well, do you think MO theory is easy for complexes? No, because, just about the hardest thing we did with MO was a heteronuclear diatomic. 2-atom molecule. You might have done a 3-atom. Did anybody do a 3-atom molecule with MO? Well, most instructors skip it. But you might have done something like water, a very easy 3-atom molecule in MO. I skipped it. I didn't want to talk about it. But here we wouldn't be describing this as an sp3d2 sp3 sigma bond. We just don't do that for this. What's the geometry of this around the aluminum? Octahedral. That holds. This is an octahedral complex, we call it. It's an octahedral complex. And so in that sense, well, that comes from that kind of valence bond type stuff. But it doesn't have to. Another thing is we have, what are the ways of counting electrons? Formal charge, oxidation state, octet. Okay, for complexes, throw those out. We aren't going to use those. For complexes, you'd say the formal charge on oxygen is, what's the formal charge on this oxygen? +1, right? And you'd say, well, we donated electron density to the aluminum, so the aluminum is going to be negative whatever, right? But we don't count it that way. For complexes, we use a totally different counting scheme. Which is like this. The way we do this is we leave, even though there's all these electrons now being donated to the aluminum, we still call aluminum 3+, and we still call water neutral. Now all these waters should have been positive, so we get +6, and the aluminum should have been 6-, according to our counting rules, formal charge, right? But we don't do that. It's weird. We just leave it as is. And so in one way it's easy because aluminum stays aluminum 3+, water stay neutral. In another way it's hard because you got to keep track of these things. You're not supposed to use it here. You can use it everywhere else but here. Okay. And so why does something like aluminum 3+, iron 3+ form complexes where something like sodium ion does not? It has to do with reactivity. What do you think is more reactive, an aluminum 3+ or sodium plus? Sodium plus is like this. Aluminum 3+ is like this in terms of size. Which one's more reactive? Aluminum 3+. Why? Higher charge, smaller size means high charge density. This is going to be much more reactive. And so when waters come along here, waters are attracted to sodium ions but are not going to react. When a water comes to aluminum 3+, what happens is there's a strong enough interaction here that water, what kind of reaction is this? So here I have my water, here I have my aluminum 3 plus. This is a very simple mechanism. Boom. Negative charge density, positive charge density, they come together and stick, bond, actually form a covalent bond. And so the water comes along here and bonds to, actually, aluminum should be a lot smaller if I draw water. I got to draw water a lot huger than this because aluminum 3 plus should be tiny. And so basically, I have my aluminum 3 plus here, and now I got a water attached to it. Like that. One of the lone pairs is now a bonding pair, and we call that, what kind of bond is that?
Coordinate covalent.
Coordinate covalent. And what kind of reaction is this?
Lewis acid base.
This is a Lewis acid base reaction. What's the Lewis base?
Water.
Water. Water turns out to be a decent Lewis base. What's the Lewis acid? Aluminum 3 plus. This is Lewis acid. Now, I told you determining the strength of Lewis acids and Lewis bases can be tricky, but in this case it's not that tricky because we're just comparing ions. Aluminum 3 plus versus sodium plus, which one's going to be a better Lewis acid? Aluminum 3 plus for sure. And so sodium plus isn't a very good. In fact, all the alkali metals, they don't form complexes like this. They just form hydrated ions. Whereas once you get to these higher charged ions, what we end up forming are complexes where the water molecules actually bond and stick to it. Well, actually, if I have aluminum 3 plus sitting out here and there are other water molecules around, what do you think is going to happen? More waters are going to attack it until there's no room to attack anymore. And so in this case, this is something we call the coordination number. The coordination number is how many atoms attack. So 1, 2, 3, 4, 5, 6. 6 atoms attacked it there. And so we call this a coordination number of 6. Octahedral complexes have a coordination number equal to 6. But oddly enough, there are 3 common coordination numbers. There's coordination numbers of 4. For example, in platinum 2 plus. How many valence electrons does platinum 2 plus have? How many valence electrons does platinum 2 plus have? 2. That's good. Did everybody get 2 valence electrons? Yeah. Platinum 2 plus. Well, actually, platinum has 2 valence electrons. Platinum 2 plus has 0. It's a little bit of a trick question. Platinum is 2, right? Platinum 2 plus 0. So platinum 2 plus no valence electrons. Platinum 2 plus is an ion. It's going to have fairly high charge density. Let's use a different Lewis base. In this case, we're going to use ammonia. Ammonia has a lone pair, negative charge density. Ammonia comes in here and binds here. Boom. How many ammonias do you think I can fit around a platinum 2 plus? Probably 6, right? But do you know how many I'm going to get around there?
4.
Only 4. And if I put 4 ammonias around here, what should I do? You remember Vesper? If I have 4 single bonds around here, what geometry should they adopt?
Square planar.
They should adopt, not square planar, they should adopt tetrahedral. Because if I have 4 groups of electrons, they want to spread apart as far apart as possible, and it should be tetrahedral. But You're right. It is square planar. So we have 4 bonded atoms, no lone pairs. Why is it square planar? Well, does valence bond theory work for these? No. Well, we got to look at the MOs. The MOs will explain why it's square planar, which we'll do later. Actually, we're going to look at the MOs at the end of the semester. Right now, we're just looking at this. This would be an example of a square planar complex. And let me show you an example of a tetrahedral complex. For example, if I had aluminum 3 plus and hydroxide. Hydroxide is a Lewis base also. And so I got some hydroxide. The hydroxide attacks the aluminum 3 plus. I can fit, actually, yeah, I can fit 4 hydroxides. Aluminum 3 plus, how many valence electrons does that have? 0. This is an example of a tetrahedral complex, a square planar complex, and a octahedral complex. And so how can I predict? How can I predict it? How can I predict if it's going to be attacked by 4 bases or 6 bases? Or 2? There's one more. Since I'm running out of time, I'm going to erase it. Silver ions. Silver ions can get attacked by ammonia also. But only 2 will attack it. Remember, we retain the charge on this. We call ammonia neutral. This whole thing has a positive charge. This is a linear. And so this is, what's the coordination number here? The coordination number is 4. Coordination number is 4. Coordination number is 2. If we have a coordination number of 2, it's easy. It should be linear. If we have a coordination number of 6, it should be easy. It's octahedral. If we have a coordination of number 4, then it's either square planar or tetrahedral. But we don't have enough theoretical knowledge now to predict which one it's going to be. You know, we could look for patterns. I'll tell you one pattern. 2 plus tend to be square planar. The 4 plus tend to be tetrahedral. Something like that. I mean, those are patterns you look at the data and you see, but we want to have a better understanding of those patterns. But anyway, going back to this, we look at this and how can we predict how many bases attack? Why only 2 here? There's plenty of room, isn't there? Can we have 4 more come in here and attack silver? Right? Or can we just have 2 more attack platinum? There's empty space above and empty space below, right? Why can't another ammonia come and bond to it? And so those are, you know, good questions that you want to be able to answer, right? But we aren't going to be able to answer those until we look at what? With Lewis acid-base reactions, we have to look at bonding, right? We have to look at the MOs in this case. For other Lewis acid-base reactions, we can use valence bond theory, like we did earlier with water and CO2. That's fine. All right, the next thing we want to do is we want to start to name these things. And the names are kind of funny. And like this one, this is called hexa aqua or hexaqua. Maybe hexaqua or hexa aqua. We might have a double vowel here, or we might eliminate it and just call it hexaqua. Well, hexa aqua iron, this one's called hexa aqua iron 3 ion. You know what this one's called? Hexa aqua aluminum Roman numeral 3 ion. You know what this is called? This should be called, well, they call water aqua. And they don't call ammonia ammonia. You know what they call ammonia? Amine. And so this is called diamine silver 1. Roman numeral 1 ion. This one is called tetraamine platinum 2 ion. This one is called tetrahydroxo aluminate 3 ion. And so this one's a little funny. This one has a negative charge, and that negative charge is an anion. So we need to know the funny names for these, like amine, aqua, and we have other Lewis bases. And so the first step is to look at the Lewis bases and then see, how do you name the Lewis base and how do you name these complexes? The next thing we look at is the metal. Some of the metals will just go by their normal name, like iron. Some metals go by like their Latin name, like cuprium, or what else is there? Orium or stanium. No, actually, it's not stanium. There's only a few. No, not that one. Gold, silver, a few others. Because, for example, if I attack silver with cyanide, I generate an anion. So when you generate an ion, you have to change the metal ending to 8. And so silver 8, does that sound very appealing? Silver 8? No. Versus argentate. Argentate sounds better. And so they use the Latin name for the anion, but for the cation they just use silver. And so there are all these little rules that we'll have to learn. And so we'll start off with looking at the Lewis bases. The Lewis bases in these types of compounds gets another name, a funny name that we'll learn. The Lewis base for these complexes is called a ligand. We have different Lewis bases depending on how many base atoms are there in the base. And so, for example, we have something called a monodentate. A monodentate would be like a typical amine, right? Just a nitrogen, and it could be bonded to other things. Like, let's go with CH3, 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 3 methyls. This is called trimethylamine. But if we have something like this, this is called ethylene diamine. An ethylene group looks like this. It's CH2 and a CH2, 2 CH2s linked together. And then we have this NH2 stuck on the end here, and another NH2 stuck on the end here. This one's called ethylene diamine, 2 words. And amine has 2 spellings. One spelling of amine has 1 M, the other spelling of amine has 2 M's. We'll look at that later. But when we look at ethylene diamine here, what's the hybridization on nitrogen? It's a sp3. Carbon is sp3, sp3, sp. These are all sp3. sp3 angles are 109 roughly. And so drawing 180 is not exactly right. What can happen with this is this. This is called a polydentate, or more specifically, this would be a bidentate ligand. Dentate, monodentate means biting into the metal. And so this is monodentate because this one base atom here attacks my metal. Like, for example, what should I do? Let's do chromium 3+. Here. Boom. Or I'll do this one as cobalt 2+ over here. This one can bite in 2 places. For example, if this lone pair here bites here, and then this lone pair here comes around and bites there. And so what happens is one lone pair attaches to the cobalt, here. And then this molecule can wrap around. Let's see, 1, 2, 3. I put too many bonds to this. Sorry, this should be. No, that's right. I shouldn't have a lone pair there. The lone pair is used to bite into it. And so here, this bites into, this is sp3. This is not the greatest sp3 drawing, but you know, it wraps around and then bites into it a second time here. And so the single ethylene diamine molecule can bond to cobalt with 2 atoms. This is called bidentate. So if you learn some patterns, we have ethylene diamine. We also have methylene diamine. Methylene diamine only has one methylene group here, methyl. It's not methyl because methylene is a CH2, methyl is a CH3. And so methylene diamine looks like this. Now, based on pattern, what would you say methylene diamine? Bidentate or monodentate? I'd say bidentate, right? It's got 2 atoms that are base atoms, right? Should bite into it. And so let's try it. And it looks good. Does that look good? Yeah? Or no? Yes or no? Well, we only have 1 minute left, so let me tell you, it looks bad. You know why it looks bad? This, what's the hybridization on this? sp3. What's the bond angle supposed to be? 109. What did we just make? A square. What's the bond angle in a square? 90. So is having it's supposed to be 109, and you're supposed to get good orbital overlap here, sp3, sigma bond. But are we getting good orbital overlap? No. When you compress the angle to 90, we're going to have a very weak bond. And so it turns out it doesn't do a bidentate. This turns out to be a monodentate because of this. 4-membered, 3-membered and 4-membered ring are highly unstable. If you formed a 3-membered ring, what are the bond angles? 60 degrees. It can be done. Have you heard of epoxides in organic chemistry? Lots of explosions with epoxides. Epoxides have 3-membered rings, 60-degree bond angles, very weak bonds, highly reactive. And so here, this is 4-membered ring is unstable. How about propylene diamine? What do you think about propylene? What's propylene? 3 CH2s. Propylene diamine, bidentate or monodentate? Bidentate. No problem, because if you look, ethylene diamine forms a 5-membered ring. Propylene diamine would form a 6-membered ring. There should be no stress in any of the bonds. Butylene diamine should be bidentate. All right, we're going to stop here. Sorry.